We've talked a bit about carbon dioxide already in previous videos, so it's time to talk more about oxygen. Oxygen, hemoglobin, and how it moves about your body. So first off, we have oxyhemoglobin. Now, oxyhemoglobin is when there's hemoglobin and oxygen bound together, which is pretty much what you're seeing right down the bottom. Hemoglobin plus oxygen equals oxyhemoglobin. But then there's also reduced hemoglobin, known as deoxyhemoglobin. Deoxyhemoglobin, like it sounds, is hemoglobin without oxygen. So deoxyhemoglobin. We've already mentioned the third form of hemoglobin, carbaminohemoglobin. That was carbon dioxide and hemoglobin bound together. So let's go through this external respiration again. We talked about it in relation to carbon dioxide, but we have to do it now with oxygen as well. So we'll go through the whole thing just to refresh it. Blown up full screen, and I'll move through it there. First off, you have the movement of oxygen. And just like in carbon dioxide, the thickness of the arrow is the amount of the actual gas moving. So oxygen simply going across and dissolving in the plasma, it happens, but there's not a whole lot. The main chunk you see here is oxygen coming into the red blood cell. So from the alveoli into the red blood cell, that's the external respiration. And then you have O2 plus hemoglobin makes oxyhemoglobin. But you notice right here, you ended up then with an extra hydrogen ion. So we'll have to figure out where that goes in a second here. So that's the oxygen. Carbon dioxide, we know it makes this whole chloride shift, and that's where that hydrogen comes into play. Because that hydrogen that was released by the binding of oxygen to hemoglobin, that hydrogen is used with HCO3-. Put those two together, what do you make? You're making H2CO3, carbonic acid. And we know carbonic acid inside the red blood cell is a very fast reaction because of carbonic anhydrase, which allows you to release carbon dioxide out into the alveoli and retain the water. But don't forget that also occurs outside of the red blood cell. That's slower though because you don't have the same exact enzyme present. You don't have carbonic anhydrase. And the last is the dissolved carbon dioxide in your plasma. Simply dissolves across, diffuses across into the alveoli, and you're good to go. So that is the external respiration. Now, for the internal respiration, we have the same idea. We need to go through for the oxygen and the carbon dioxide. So again, throw up full screen so you can see what's going on here. So we know we can see now internal respiration is the blood into the different tissues of your body. The larger, thicker red is the oxygen coming off of hemoglobin right here. So therefore the oxygen dissociates and you're left with the deoxyhemoglobin. You still have some oxygen simply dissolving from the plasma across. Bring in the carbon dioxide. We have carbon dioxide also that's transported just as dissolved in the blood plasma. But then we have that same reaction. Carbon dioxide plus water goes to H2CO3, carbonic acid. And then that quickly is dissociating into HCO3- and then a hydrogen ion as well. But in the plasma that's slow, inside the red blood cell that's fast. There's a much faster reaction down here in the red blood cell. But no, again, pay attention. When you do this in the red blood cell, the dissociation of HCO3- here goes out into the plasma. That helps buffering the blood. But to remove that negative ion, you have this whole chloride shift occurring. Chloride comes in. By doing that, you maintain those negative charges in and out. And the extra hydrogen ion, you can see right here, is going to bind with hemoglobin to make your deoxyhemoglobin, your reduced hemoglobin. So a couple of different things going on depending on if you're at the internal respiration like here, or the previous slide's external respiration. They both have the movement of oxygen and carbon dioxide, and it's pretty much the same processes, just in reverse order. internal respiration has oxygen going into the tissues, while the external respiration had oxygen going to the blood. And then just the reverse for carbon dioxide. So O2 and hemoglobin. You can see the whole list here. Partial pressure of O2, temperature, blood pH, partial pressure of CO2, and even the concentration of BPG. All of these are going to impact the rate of loading and unloading of O2. You're saying, well, what is loading and unloading of O2? You're looking at how the oxygen binds to hemoglobin and then how it unbinds from hemoglobin. So looking at that back and forth. What we have here is going to be an oxygen saturation curve. Now I'm going to blow this up full screen so you can really see the details of what we're looking at. The bottom of the graph down here is your partial pressure of oxygen, while the y-axis here is the percentage of O2 saturation of your hemoglobin molecules. So for example, up top here, 100% saturation is meaning you have all 4 oxygen molecules bound to hemoglobin, because hemoglobin can bind a maximum of 4 oxygen molecules per hemoglobin. Down here we're looking at 2 bound. That means that's 50% saturation. So the 2 different points of interest here. We have 1 point right here and 1 point right here. Now I'll leave the top point left alone for that one. What that top point is showing, that is when you hit the 104 partial pressure at the bottom. Now yeah, it's showing there's 100 right there, but it's just a shade past the 100 actually. Because remember, in your lungs, it's 104 millimeters of mercury partial pressure in the alveoli. So what's happening then, at that case, you're reaching pretty much 97-98% full saturation of your hemoglobin. You never quite reach a pure 100%, that's just theoretical. I mean, I guess you could if you're in a high oxygen environment, but the average person just outside breathing, 97-98% is your fully saturated state. But then look at this other one over here. That is now the partial pressure at 40, so the oxygen partial pressure is 40. That's what's happening inside of your blood vessels and your organs. So that's what's out and about in the body. It comes back in, picks up, gets higher oxygen concentration, goes out. Even at that partial pressure of 40, which is what's down in your muscles and the rest of your systemic circulation, notice that your saturation is still sitting up here, give or take about 75% saturated. You're looking at still 3 of the 4 molecules filled. So that's the low level. That's the amount you're already coming back after being used. So the nice thing here is when you're looking at this large amount from 40 all the way up to 100 or 104 millimeters of mercury pressure only changed the saturation about 25%. It's when you go below that, down here, that very quickly small amounts of change in the partial pressure have drastic amounts of change in the oxygen saturation. So the way this works is you have a very large amount of change in partial pressure, 40 up to 104, but it only changes about 25% saturation. Anything below that, anything below the partial pressure 40, has a much steeper curve to it, which means it has a much faster drop-off. So what we're looking at here in this curve is these small changes initially of partial pressure have very large drastic changes in saturation. But then you get to larger changes of partial pressure, where we normally reside in your resting state, only have small fluctuations. The idea is this is really helping out to keep your oxygen saturation at higher levels, unless you're exercising. Then when you start exercising, things change a little bit. This is the at rest we're looking at. All right, this one's looking at the saturation curves for elevation, altitude. Notice that we're showing there's 2 main points here, 100 and 80. 100% partial pressure is sea level, 80% partial pressure, we're saying that's up in the mountains. But even with that 20 partial pressure difference, look up top here. Difference of 3, 4, 5% saturation, that's it. But if you've ever been up in a high elevation, think of up top of the Rockies, 2-mile elevation, you'll notice that that does have a pretty quick impact if you're moving around. Now, if you're sitting, not too much of a problem usually, but try climbing even a flight of stairs, going for a walk. You'll notice how quickly that does change things. Because you're not at rest, which this is showing, you're active. Your body's using more oxygen. Therefore, you're dropping the partial pressures and the saturations faster. So if you're at a higher altitude, you have a decline in blood O2. That's going to trigger increased production of EPO, that's erythropoietin. Remember back, erythropoietin is the hormone from the kidneys that stimulates red blood cell production. So by having a declined O2 for a period of time, this isn't 5 minutes, we're talking a longer period, it'll increase your erythropoietin. What that does is your red blood cell numbers start to slowly increase. It's not a drastic jump, but it slowly increases more and more and more until your body's basically compensating by having more red blood cells to carry the oxygen at the lower saturation levels. Now, if we go into exercise though, again, look at the graph. We still have our same partial pressure 40 at rest, 75% saturation. But if you're exercising, your muscles are using more oxygen, your tissues are using more oxygen, which means the partial pressure inside your blood and your tissues drops. You might end up with a partial pressure down here of about 20 millimeters of mercury oxygen. That 20 millimeters of mercury, if you notice, dropped all the way down to just below 40% saturation. So only this small 20% pressure change ended up with a give or take about 35 to 40% saturation change. So the lower partial pressure you get, the larger and faster the saturation changes will occur. And that's why when you're working out and exercising, there's a limitation of where you can go, because you can only so quickly get oxygen back to the tissues to keep them functioning. So a little about how the oxygen saturation curves are working at rest, at altitude, and during exercise.